Good morning. This is lecture number 36, module 6, matrix analysis of plane and space frames. If you recall, in the last session we covered the reduced stiffness method. We will continue with that method and also complete the flexibility method as applied to plane frames. This is covered in the chapter on plane and space frames in the book on advanced structural analysis. So this is the reduced element stiffness method. You know that the size of the plane frame element stiffness matrix is 3 by 3. We've done a few problems. This is how you do the transformation, the TD matrix in the reduced element stiffness method. And now let us look at a problem with sloping legs, which is actually a complicated type of problem when you apply the reduced stiffness method. So you have to intelligently identify the sway degrees of freedom. We've discussed this earlier, and you need to express the chord rotations in terms of the identified sway degree of freedom. So let's look at this problem which we've solved earlier by the more rigorous method. So let's solve this by the reduced element stiffness method, and let's take advantage of the fact that we can ignore axial deformations. We have solved this problem earlier by the slope deflection method. What is the degree of indeterminacy, kinematic indeterminacy? The shortest needed. Degree of kinematic indeterminacy refers to the active global coordinates. The absolute minimum when you don't have axial deformations.
8.
Okay.
5.
At the supports A and D, do you need to have anything? No. We don't even bother about finding reactions. We do the minimum work. So at B and C, how many do we have? At each of them,
2.
you have a rotation at B, you have a rotation at C, and you have just one sway degree of freedom. That's what we did in slope deflection method. Remember, theta B, theta C, and delta BC, correct? But we've done this problem by the conventional stiffness method. There the degree of kinematic indeterminacy was at B and C you had each 3 degrees of freedom, 3 plus 3. You also had a rotation at A and D, it was 8. So we are reducing 8 to 3, but we are ignoring axial deformations. Okay, that's a major reduction. Okay, the method of solving is, as we have discussed earlier, the steps are the same, plus we take advantage of the fact that we limit the considerations only to active degrees of freedom, because we can always get the support reactions at the end from the free bodies. So let's do this problem. Okay, so I've got 3 degrees of freedom, global coordinates 1, 2, 3. That's all I need. Local coordinates, again I take advantage of the fact that there is a hinge at D, A and D. So my 2 degree of freedom beam model will now become 1 degree of freedom model. What I have achieved is a massive reduction in the quantum of work. I am not going to use a plane frame element, I am using a beam element. A plane frame element has 3 degrees of freedom in the reduced formulation, but I am not worried about the axial degree of freedom. So the 3 becomes 2, the plane frame element becomes a beam element, and I am using that formulation for element number 2 because there is a fixed end force coming in there, there is an intermediate load, and B and C are not hinged. But for elements 1 and 3, I take advantage of the fact that I have a hinge support at the ends A and D where the bending moments are 0, and so you know I can take advantage of a reduced stiffness. What is the element stiffness for that, flexural stiffness? 3 by L. So I just need 1 degree of freedom, which I have marked as 1 star. Is it clear? So with this I can proceed. I first need to write down my TD matrix, TDA matrix. Will you try that? Okay, to do that you have to be very careful. When you are dealing with sloping legs, you have to correctly express the chord rotations in terms of the sway. So the displacement D1 corresponds to the delta in this figure, right? The figure at the bottom is a generic figure. So you have chord rotations of delta by the height for the elements 1 and 3, right? And for the element 2 you have to work this out using trigonometry. It turns out to be, as shown in that formula, delta tan alpha plus tan beta by the span L. I am not going through this all over again because we did exactly this when we did the slope deflection method, right? So if you plug in the values of tan alpha and tan beta, because the dimensions are shown there, you will get the chord rotation for the element 2 as plus 27 by 36 times the sway D1. Okay, just plug in the values of tan alpha and tan beta. The span of that element BC is 3 meters. So you will get this. Shall we proceed? We have done this earlier, it is just a repetition. We put a positive sign because you are getting an anti-clockwise chord rotation for element 2, but please note for elements 1 and 3 the chord rotation is clockwise, okay, chord rotation is clockwise. So and it is given by delta by the respective heights. Now can we write down the TD matrix? We can. So the TDA matrix for the 3 elements are as shown there. If you apply D1 equal to 1, then for the first element the chord rotation is 1 by 4. It is a clockwise chord rotation, you get equivalent anti-clockwise end rotations, and it will be plus 1 by 4 because anti-clockwise is assumed to be positive in the sign convention. The same is true for the element 3, so you get 1 by 3 because the height is 3 meters, okay. As far as the element 2 is concerned, it is 27 by 36, right? We just worked it out, no, phi 2, it is 27 by 36. If you expand it, sorry, it is 17 by 36, it turns out to be 0.4722, but it is a clockwise rotation, so your equivalent end rotations will be, sorry, it is an anti-clockwise chord rotation, you get clockwise equivalent end rotations, so it turns out to be minus. This is the only difficult part, that first column in your TD matrix has to be very, very carefully written because it is totally dependent on your correct assessment of the chord rotations, both magnitude and direction. The others are simple. If you put D2 equal to 1, we are now talking about the second column in the TD matrix, then you will find that you get it will affect only elements 1 and 2, the right end of element 1 and the left end of element 2. So you get, and element 3 is unaffected, so you get 1 1 0 0, and similarly for D3. Is it clear? This is easy to generate. Can I proceed? Okay, you have got your TD matrix. Now you have to carefully write down your fixed end forces. We did this earlier, and remember we just calculated the fixed end moments, but here you have to be careful because you have only 3 degrees of freedom, D1, D2, D3, and you do not have those vertical forces which we put on the last occasion, right? There are no vertical degrees of freedom. So you have to manage with rotational degrees of freedom and a sway degree of freedom. You have to handle the problem in that framework. So how do you do that? Well, first of all, from this analysis you can find out that there are going to be no fixed end forces for elements 1 and 3. Why? Because there is no intermediate load. And for element 2, the fixed end moments are 30 kilonewton meter minus 30 kilonewton meter, and there is no axial force. Okay. So this is what you get from this diagram, but how do you include the effect of axial force here? You have only 1, 2 and 3 in the global coordinates. How do you transfer this understanding to equivalent joint loads in the global coordinate? What is, in other words, what is F1, F2 and F3? F1F, F2F, F3F. What is F2F? F2F is plus 30 because it comes from element 2. What is F3F? Minus 30. What is F1F? What is F1F? It's not 0. If it's 0, then you make a mistake. What is F1F?
40.
Yeah. You look at what's happening at B and C. You have restrained those degrees of freedom. At B you get a horizontal reaction to the left of 45 kilonewton. At C you get a horizontal reaction 40 kilonewton. What's happening to the whole beam? So you will get a net force of 5 kilonewton acting to the left or right?
Left.
Okay, to the left you are right, but when you find the net loads you have to oppose everything, you put a minus. Have you got it? So that's it. Look at this, it's completely different from what we did earlier, and you are going to get the same results. You see, there are so many different ways of solving these problems, but sloping legs problems are tricky, they are notorious. Students generally make blunders, practicing engineers do it, but luckily for you today you have nice software which is a black box to most engineers. You just feed in the input and you get the output and you hope all is well. But we are learning, and we are learning to do these problems by different methods, including flexibility method, and we know one thing for sure, the answers have to match. The answers have to match. We will expect some difference between ignoring axial deformation case and including axial deformation case, and that will be a little more pronounced when you have sloping legs. Okay, we will see that. Apart from that, you should get the same answers we got when we did the slope deflection method. Okay, so we proceed, we write down the element and structure stiffness matrices, very easy to write down. EI by L for all those values are known, and 3 EI by L is what you will put for elements 1 and 3, and for elements 2 it is the standard 4 EI by L, 2 EI by L, 2 EI by L, 4 EI by L. Is it clear? We can generate this and then carry out these products and do the final superposition and assemble all the matrices, you will get this answer. Okay. This is, I am going fast because you know how to do this. Now you are ready to take any load. You give any D1, D2, D3, you get any F1 minus F1F, F2 minus F2F, F3 minus F3F, that is your net load vector. You will get the solution with the power of this matrix. So we will do that. We will invert this matrix, plug in those values of 5, minus 30 and plus 30, you have got those answers, okay, and that is what your deflected shape looks like. Now you will find that that deflection, if you compare with the earlier result, has a little discrepancy, okay, but that's, you have to live with that because that's the approximation you get from ignoring axial deformations, but this is exactly the answer you get when you do slope deflection method, okay, right. It is also exactly the answer you get from flexibility method ignoring axial deformation. If you do a strain energy formulation, you will get this. Then you find the member forces and you draw your final bending moment diagram. The bending moment diagrams do not change significantly, it is only the deflection that changes. Okay. You know how to handle this problem? You have got a similar one in your assignment, you have got a hinged support, you have a support settlement also, but luckily for you, you do not have sloping legs, they are vertical. So please do those two assignment problems and you will get a good understanding of stiffness method. We now look at the last remaining topic of flexibility method. Not applied commonly in practice for frames, okay. We do it for beams, we do it for trusses, for frames it is not common, but the logic is the same and at least conceptually let us learn it. You will find that in your assignment I have not given a problem on flexibility method. In your final examination it is unlikely I will ask you a question for plane and space frame, but let us just go through the theory and see how it works, okay. First you need to identify the degrees of freedom. You know that it is the same as you use for the reduced stiffness method, 3 degree of freedom system. You can generate the flexibility matrix from first principles, you apply 1 unit load at a time. Here you apply loads. You can do one thing, you can take your stiffness matrix and invert it, you will get the flexibility matrix, but that is no fun. Flexibility is for people who want fun, because you want to understand exactly what is happening. So here when you pull it you are not going to get any moments, it is just like an axial truss element. You know that the deflection, the lateral elongation you get is the extension in that element, it is the flexibility, axial flexibility L by EA, clear, and that is your F1 star 1 star. Next you apply a rotation, so now you are doing what you did for the beam, you get rotations of L by 3i and L by 6ei, one will be anti-clockwise, the other will be clockwise. You do not have any axial change in length, that is an assumption we are making, because we are saying that the flexibilities do not interact, the axial degree of freedom and the flexural degrees of freedom are independent. That is an assumption we are making here. We will see through that assumption in the next module and we will bring in that interaction. Okay, right now we accept this and you can do it at the other end and you can generate your flexibility matrix. Very easy to remember because you know what you did for a beam element, you know it is L by 3i minus L by 6ei, L by 3i and minus L by 6ei. You just have to add the axial stiffness as you did in the stiffness method, L by A. Okay. Then you do the transformations and standard procedure. Let's this is for the beam element. For the frame element it will have 3 degrees of freedom, the rest of the procedure is the same. You generate the structure flexibility matrix, you write the compatibility equations, you solve and find the redundance, then you can find the joint displacement if you want to. In the stiffness method you had no choice, you had to find dA to proceed to get the member forces. Here you do not need to find dA, you by solving that second equation you get the redundance. If you can draw the free bodies and get your member end forces, you finish everything. So this is the procedure, the displacements come at the end. Okay, now let us do just one example with and without axial deformations. Okay. Now please note, when we did the method of consistent deformation, when we did the theorem of least work, we assumed axial deformations were negligible. So we are now doing for the first time flexibility method with the axial deformation. So let us see how to do that. What is the degree of kinematic? Here we have put in 2 complications, okay, just to see how to apply this method. One is you have a support settlement, the other is you have an internal hinge. Okay, so if you did not have that hinge, you know that the degree of static indeterminacy is 3, that hinge brings your moment release, so it drops to 2. Now you can choose your 2 redundants. Which would you choose? You want the primary structure to be a cantilever? Then that third element will be dangling in the air. It will be unstable. Can you please think carefully? I mean, you prefer keeping the fixed end A as fixed end, right? That's what you meant by cantilever. Mind you, you can still do that, but at D you don't remove that support. What kind of roller?
Guided.
You want the roller to roll vertically or horizontally?
Vertical.
You have a choice. Not only that, you can choose any two. So let's do something interesting in the next slide. Okay, so I am going to choose my redundants x1 and x2 as the vertical reaction and the fix and the moment at the support D. Okay, which means I have to, in my primary structure, I have to release those two corresponding restraints to displacement. So what's the support I will put there? Huh? There you are. Put a roller in the vertical direction. Okay, put the roller in the vertical direction and number your coordinates appropriately. So we know, you know that we have always put the redundants at the end of the list. So we have 1, 2, 3 degrees of freedom at B, 4 and 5 at C. There is no rotational degree of freedom, you can't bring it there because you do not have a unique rotation there. Each of those two elements will rotate by a different amount. Okay, so you do not number it. We did the same thing in the reduced element stiffness method, but here we add 6 and 7 as redundant coordinates. So this is how it will look. If you write the force vector, we separate Fa and Fx. Fa is the load applied is 50 kilonewton because there is a horizontal load at B. Rest of the quantities are 0 and you have x1 and x2, x1 and x2 are unknown. Any question? Okay. You also have to write down the compatibility equations to solve for the unknown redundants x1 and x2. What is dx? What is d6 and what is d7?
D6 is -1.
Right, d6, that is where you bring in the support settlement. d6 is minus 0.01 meters and d7 is 0. Yeah, you have a question? I am not ignoring. To go back to the question, we said we will first include, then we will ignore and then we will see the difference. Okay, so we will remove that in the next phase. Right now we will include it. So the procedure, first write down the force transformation matrix, find out the equivalent joint loads. Okay, you have to do the, so this part is borrowed from stiffness method, which is unfortunate because you are, so flexibility method is not able to stand on its own. It has to borrow this concept because you just can't handle intermediate loads in a matrix formulation. Okay. Unassembled element flexibility stiffness matrix, structure flexibility matrix, TF transpose F star TF, write down the displacement equations, solve the compatibility equations, get the redundants, get the member forces, and if you wish, get the joint displacements. Okay, the procedure is very clear. The items 4 and 6 emerge from those set of equations. Okay, from the second equation you get the redundant, from the first equation you get the joint displacement. We have done this earlier, the procedure is the same. So this is interesting. Let us generate the TF matrix. TF matrix has two parts, TFA and TFX. How do we do that? You have to apply unit loads at a time. So it will look like, if you apply unit load F1 equal to 1, take that huge structure and apply, do you think anything will go to the support D? No. So it will be only element 1 will behave like a cantilever, right? Am I right? If you apply F1 equal to 1 and no other loads, so then you need not draw the whole frame, you just pull out that cantilever, you have got those results, right? So I am going to demonstrate here how to generate the force transformation matrix. Okay, F star is F star F plus TFA times FA net plus TFX times Fx net, right. We will work out that FA net, Fx net later after we handle the fixed end forces, but right now our task is to write down TFA and TFX. Okay. So I have written down the first 3 columns corresponding to F1 equal to 1, and I will show you F2 and F3 shortly, but is you look at that first column 0 4 0, is it right? Because only the first element will have non-zero items, second element will not be affected, third element will not be affected because this is a cantilever action for element 1, agreed? So that is why you got zeros for here. I am applying this load on this structure here, only this element gets affected, elements 2 and 3 remain unaffected. So the first column corresponding to F1 equal to 1 will have 0 0 0 0 0 0 for elements 2 and 3. So element 1, these are the reactions I get. If you go back and I have not shown the element coordinates, the element coordinates would be, what would they be? They will be 3 by 3, right, they will be 3 by 3. So you will find that the first item here, what does this correspond to? What does F1 star correspond to? Axial force. Will there be any axial force in this element? No, that is why I put 0 there. Second element corresponds to what? Moment at this, well, it depends on how you put your element, but it's here, 4 here, right? And the third one, moment at B is 0, right? It depends on start node, end node. I put start node at A, so anti-clockwise is clear, so it's 4. Now let us take the second case, F2 equal to 1. Can you try drawing the response for F2 equal to 1? I am going to show it to you. F2 equal to 1 means you are going to, what is going to happen if you apply F2 equal to 1? You will just get one axial force in first. So that is a simple thing. So does it make sense? You get just one, here and the rest of it are all zeros, clear? Very easy to fill up. Next one, can you try F3 equal to 1? F3 equal to 1. F3 equal to 1, will it affect element 1 only or?
Only 1, but rigid body displacement for 2.
That's it.
It will affect only element 1. Try drawing it. Will you get any reactions at D when you apply that unit moment? No. No. I will tell you one way to understand. Remember when we talked about internal hinge, usually you have a parent-child relationship. Now clearly element 3 is a child, it badly needs elements 1 and 2 for it to hang on to for its own dear life, right. So the child cannot take loads when the parent is loaded. When the child is loaded, you will get something in the parent, let that be very clear, right. So you can quietly remove the child from the picture and look at the parent. Parent is a cantilever. Now if you apply a moment at joint B in that L-shaped cantilever, do you think anything will go into element 2 and 3? No. So this is flexibility method. You really have to enjoy the physics of the problem and get the answer. So you just have to draw this.
Local coordinates.
Yep.
One actual degree of freedom and 2 moments in
Right,
element 1.
right.
But element 2 has 1 actual degree of freedom and 1 moment only.
No, they are all frame elements, all are identical, all have 1 star as the axial, and because there is going to be an axial force in that element. Sorry?
In element 2, there are no.
We do not take advantage of it here. We do not take advantage of that hinge here because that we will do when we ignore axial degrees of freedom. You understand? This is. Here we are not taking advantage of the release there. You can do it. I am not taking advantage in this case, but I will take your suggestion in the next case where we ignore axial deformation. So your point is valid. I can actually reduce the degrees of freedom for elements 2 and 3. Right now I have not done that. It's okay, I will still get 0 moment there. So your point is good, we will do it later. Is it clear? Now I will go faster. If you apply F4 equal to 1, again the child is not affected, so I have not shown the child here. The child is element 3. So can you generate the middle part as I have shown here? You can work it out. Next one, apply F6 equal to 1 and F7 equal to 1, you get the remaining parts. Okay, here the child is being pulled and the child is hanging on to the parent also gets pulled. Clear? So you have got all 3 elements activated when you apply these loads. These are simple things, this is a statically determinate system, you can write down those forces, but it is fun writing down the TF matrix. Now just look at this complete matrix. What we are saying is, we have written a set of equilibrium equations. If someone gives us this vector, which is the fixed end force vector, someone gives us this load vector including the redundants, we have drawn it for a primary structure. The redundants are treated as loads on the primary structure. F6 and F7 are loads on the primary structure. Is it clear? We get the bar force, get the member end forces, and we will do this in the last step. Okay, so how do we proceed now? We have to write down the fixed end forces. Okay, elements 1 and 3 have no fixed end forces. So these are the local coordinates, by the way. So this analysis we have done earlier, we have done it for the reduced element stiffness method. Here you do an analysis where you do not get a moment at C, which means you have to treat it like a propped cantilever to get the equivalent joint forces. Is it clear? You get the vertical reactions and write down the F2 star F vector. You have only one moment there, because here you are accounting for the fact that at C there is a hinge, so you do not get. So does it make sense now? I have taken care of the hinge, but I am still keeping my full fledged 3 degree of freedom matrix, but I will take advantage in the next situation. Okay, so I have got my fixed end force vectors. For the first and third they are null vectors. For the second one I just have one moment there, 111.11, and that is anti-clockwise, and I can write the FF vector. Okay, clear? Next I should get the net joint loads, resultant nodal loads. So that is F net is FA minus FFA and Fx minus FFx. I just do this substitution. When I write the second one, I have to, that is where I bring in those forces. You see, this is given to me, this is right in the beginning. Okay, I have 50 kilonewton load and I have x1 and x2, I do not know. This is my FA Fx vector. This is my fixed end force vector, which I compute by inspection. By inspection, if I go back here, I see that not only this will contribute to F3 and these two reactions will contribute to F2 and F5. Is it clear? That is how I get these two quantities here. Does it make sense? And they are pointing upwards, so they are positive, but I put a minus sign, and so now I get the final picture. This is the structure I am going to analyze. Is it clear? It is completely taken care of the effects of the intermediate loads. How do I analyze this? I first generate my element flexibility matrices. I have taken them all to have this format. It should be L by EA, okay, and all these values are known. You can generate the flexibilities. What do you do next? Generate the structure flexibility matrix. You have the unassembled flexibility matrix by putting them in a diagonal form. You have the TFA matrix, you do that product, you will get Fxx, it is a 2 by 2 matrix which you can generate. Please note, when you actually do it on MATLAB or on a computer, you have to be careful when you deal with flexibilities, because stiffness values are going to be large when you write in kilonewton meter units. but the reciprocal of it, the flexibilities are going to be very small. So if you work with the absolute figure, you will have massive rounding of errors, so you have to work with significant figures. So you have to cleverly take out 10 raised to minus 6 outside, so you get large numbers inside and you do not truncate those digits. This is what you have to be careful when you deal with flexibilities. Is it clear? In stiffness you do not really have that problem, but in flexibilities you have. You understand, if you have this quantity and you wrote it in decimal format with 10 raised to minus 6, you might write it as 0. So 9800 becomes 0 because you're used to writing by hand, point not now, you get tired of writing so many zeros, so you say maybe it's meaningless and you put 0. Is it clear? So be careful, because you need to work with significant figures. So you do this, get the inverse of it, and you're ready to do the final calculation. Similarly you can generate fxa and fxat, all this can be done through matrix operations. Now you find the redundance by solving that second equation. You do not have any temperature effects or construction errors, so you do not have any initial forces here. You plug in those values and you finally get the fx net. Okay, so you get x1 and x2 in the last step. X1 and x2 is 39 kilonewton and 74.18 kilonewton. Find the member end forces. You remember those large equations we generated with the TF matrix. Now you are in a position to put in all those unknown values. You get the final end forces exact. Then you draw your, if you compare with what we did earlier, in the exact method, the conventional stiffness method, or the reduced element stiffness method without axial deformation, you will get these answers. Absolutely no error till the 6th or 7th decimal place. Okay, it's exact. Okay, then you draw the free body diagrams, draw the bending moment diagram, and again remember we said that you can get the deflection straight away. You are really interested in the sway by recognizing that CD behaves like a cantilever. We have done this earlier, but if you still want to work out displacements for the hard way, you are welcome to do so. Do this calculation and interpret the results. You will get exactly the same values we got earlier. Okay, so with this we complete the flexibility method, including axial deformation, which is something new you have discovered. You have not done it earlier. You had not done it in method of consistent deformation. You had not done it in theorem of least work or column analogy method, that is another method. Now let us see how to take advantage of axial deformation. One way to get the solution if you are writing a program is put EA tending to infinity there, large value of EA, you will get the result of solution without axial deformation, because if axial rigidity is infinitely large, axial deformation is small, that is what you get. But let us do it this way now. What is interesting is your degrees of freedom now reduce. You had 7 earlier, now you have 4, okay, for reasons which we have explained earlier. So you have only 1, 2 and 3, 4 corresponds to your restraint degrees, your redundant degrees. Also for the beam element we will take the advantage that you had pointed out, the 2 degree of freedom beam element for 1 and 1 degree of beam elements for 2 and 3 can be used in place of frame element. So we are going back to beams and we are taking advantage of the modified flexibility. So we can do that. For element 1 you still have 2 degrees of freedom, but because we want to take advantage of the internal hinge at C, I put a roller support there, so I have only 1 degree of freedom, and my FA and FX vectors are easy to calculate, it is smaller, much easier to work out. Dx is the same, only thing is earlier we wrote D6, D7, now we write D3, D4. Force transformation matrix, much smaller, much easier, F1 equal to 1, F2 equal to 1, same results, these two do not change, F3 equal to 1, F4 equal to 1, same, only we have renumbered them. F6 became F3, F7 became F4. Your size of your TFA matrix is shrunk to a nice compact size, right? You can interpret the results very easily. You got your TF matrix. Find the fixed end forces exactly as we did earlier. There is no change in this, only your size of your vectors have become smaller. You got rid of things that were not required. You are dealing with the same system. Element flexibility matrices, F1 star is the same as we got earlier, but for elements 2 and 3 you take advantage of L by 3EI. Okay, this is a clever trick you can do. 3EI by L for stiffness, L by 3I for flexibility. So you get, so I have, for the first time I have introduced this symbol F star tilde because it is like K star tilde. It is different, you know, you are working with a reduced flexibility. Right, generate your flexibility matrix. This is the unassembled flexibility matrix, okay. Then you do the operation and generate your, you can do them separately. Fxx is Tfx transpose F star Tfx, and Fxa is Tfx transpose F star Tfa, Faa is Tf transpose F star Tfa. Is it clear? Or you can deal with it all together and then partition it at the end, but this is much easier to handle. Find the inverse of your Fxx matrix, find your redundants, okay, plug in those values, you get your solutions as 39.048 and 74.286 now. What did you get earlier? 39.059 and 74.182, big deal. So that is why we do not waste time dealing with actual deformations, okay. The errors you make are negligible, and in the context of what we discussed yesterday, this is certainly acceptable, this kind of, because there are going to be much larger errors in reality, okay. Finally, member end forces, plug in those values as we did earlier, find the displacements if you wish. Now you get the same sway at both ends, but it is very close to what we got earlier, and the deflection at C earlier was 10.07 mm, now it will go down only as much as the support D goes down. Is it clear? So we have tackled this problem in many different ways, we are very clear what is going on. Proof of the pudding is in the eating, which means the answers should match, completely different methods and same answers. Finally, your free body diagrams, bending moment diagram, compare these two diagrams, exact with axial deformations and without axial deformations. It is all the same, I mean you are making errors in the decimal places, not worthwhile doing it. So powerful methods, when you do manually, do them the easy way out. When you are writing a program, do not do flexibility method, do the stiffness method. You have a choice, reduced element stiffness method or conventional stiffness method. With this, actually we have completed everything except space frame, which are really tough, but I am trying to make it simple. Again, you do not need to do anything in your assignments or exams, but let us get a taste of it. It is like moving from 1 dimension to 2 dimension to 3 dimension. The concept is the same, but you have to really think, especially if you want to do the reduced method, which you should learn to do manually. So we will cover it, I am not expecting to do any examples, we will do this in tomorrow's class. After that, the 7th module again is an exposure I want you to have, okay. I want you to be present, not so much to learn to solve it because it is really advanced, okay. It is second order analysis, but you should have a flavor of it, and those of you who are interested can actually sit and solve those problems. I am planning to finish that in 3 sessions, and then we will have one last concluding session, okay. So we are nearing the end of this course. Thank you.